Hey everyone! Today we're going to dive into an interesting problem, which is generating all of the possible sequences of throws in a game of rock, paper, scissors. This is going to help us explore the concept of recursion, which is a key tool that you'll use in solving problems like this. And by the end of the presentation, you'll understand how to use recursion to generate all possible outcomes for any number of rounds in rock, paper, scissors. Let's get started. So today we're briefly going to cover recursion, then we'll define what this rock, paper, scissors problem is and dive into solving it with a recursive approach. We'll go over the pseudocode, walk through the code, discuss performance, and then wrap it up with some key takeaways. Recursion is a technique in programming where a function is actually calling itself to solve smaller parts of a larger problem. So a helpful analogy here is the idea of Russian nesting dolls. Imagine you have a large doll that contains a smaller doll inside of it, that contains a smaller doll inside of it, and an even smaller doll, and so on. Each doll is a smaller version of the larger one, and just like how recursion is repeatedly breaking down a problem into subproblems, that's what you're seeing here with those Russian dolls. Eventually, you get to the smallest doll, and that's going to represent the solution or the base case. Recursion has two main components. The base case, which is the condition that stops the function from calling itself indefinitely, and the recursive case, where the function actually calls itself to work towards the base case. Now that we understand the basic concept of recursion, let's apply it to a simple example of a factorial. So a factorial is represented by an exclamation mark after a number, and it refers to multiplying a number by every positive number less than itself all the way down to 1. So if you look at 4 factorial, that would be written as 4 exclamation point. That will mean multiplying 4 by 3 by 2 and finally 1, which gives us 24. Similarly, 5 factorial, or 5 exclamation point, would be 5 times 4 times 3 times 2 times 1, which equals 120. Let's first look how we would calculate the factorial of a number using our normal iterative approach. In this case, we would use a for loop. For example, if n is 5, the function will multiply 1 times 2 times 3 times 4 and then 5 to get the factorial result. This is just a straightforward approach. It doesn't involve any recursion. It's just looping through a sequence of numbers and accumulating the result. Now let's look at the same problem using recursion. This time, instead of using a loop, the function will call itself with a smaller version of the problem until it reaches the base case. In this example, the base case is when n is equal to 1. That's when the function returns 1 and stops. Otherwise, the function will call itself with n minus 1, meaning it continues multiplying n by the result of factorial n minus 1 until the base case is reached. Let's take a look at what that would look like if n equals 4. The function will first call factorial 4. And since n is not equal to 1, we'll enter the recursive case down here, which will be 4 times factorial of 4 minus 1, which is factorial of 3. So that first call is giving us 4 times factorial of 3. The function then calls factorial 3, and again, since n is not equal to 1, it's going to return 3 times the factorial of 2. Next, factorial 2 will then call factorial 1. So 2 times factorial 1 is what's happening in our third call. And then our final call is our base case, because factorial of 1, n does equal 1 here, so we're going to return 1. So now we have 4 times 3 times 2 times 1. And the recursion will begin to unwind as we go back up this call stack. So for factorial 2, that is equivalent to 2 times 1. Next, we'll go up to factorial 3, which is going to give us 3 times 2. Next, we'll go up to factorial 4, which was our first call, and that's going to be 4 times 6, which will give us our final answer of 24. So as you can see, the function is repeatedly calling itself until it gets down to its base case, and then it multiplies the results together as it returns back up the stack. Let's briefly discuss two common types of recursion. So there's direct recursion, and then there's helper function recursion. Starting with direct recursion, this is when the function is calling itself directly, like we just saw in that factorial example. The function will start by solving one part of the problem, and then the remaining part is passed back to itself. So here's another example of that, a countdown. And in this code, countdown keeps calling itself until n reaches 0. You can see here that the base case will return an exit once n equals 0. And then here, after printing out the number n, the recursive case will subtract 1 from n and continue to call itself and count down until n equals 0, which is our base case. This is direct recursion. Sometimes it's useful to have an external function that's managing the recursive calls and keeping track of state. This is often called a helper function. Let's take a look at an example. In this example, we want to find all even numbers in an array and add them to a result array using recursion. To do this, we're using a helper function, which allows us to manage the state of the result array throughout the recursive process. And here's how this approach works. So first, we're going to start by initializing an empty result array before the recursion begins. This ensures that the result array exists outside of the recursive function and isn't recreated with every call. So inside this find even numbers function, we're going to create our helper function. And this is where we will do all of the recursive work. So it'll take in one parameter, index, which tracks where we are within the array. The base case is simple. When the index reaches the length of the array, we're going to stop the recursion because we've already processed all of the elements. On each recursive call, the helper function is going to check if the current element is even by dividing that element, so modulo 2, and seeing if that equals 0. And if it is, we're going to push that element to the results array. Then the function moves on to the next element by calling itself with the next index. And you can see that the initial call of the helper function is starting that index at 0, so that when it begins its check of the base case and then the recursive case, it starts at 0 and goes up through the array length until it returns its final result after hitting the base case. And this structure is valuable because the helper function is able to use the same result array across all of these recursive calls. If we didn't have a helper function and instead passed the result as a parameter, it'd be difficult to keep track of it without accidentally resetting it on every recursive pass. This helper function preserves the state of the result array, which is outside of it, which allows us to accumulate those even numbers as we move through the array. And this is a big advantage over direct recursion, where it's harder to manage that ongoing state. So today, we're going to be solving a problem where we need to generate all possible outcomes of throws that a player could make in the game of rock, paper, scissors, given a certain number of rounds. We're going to write this JavaScript function called rock, paper, scissors, and it's going to take in rounds, number of rounds, as an input. The output of the function will return every possible sequence of throws that a player could make. So for example, the output would include combinations like this: rock, 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 paper, rock, rock, scissors, and then move on to the next iteration: rock, paper, rock, etc., until you have all possible combinations. So let's start by pseudocoding our problem out. So let's start by declaring the function. We'll call it rock, paper, scissors. And we're going to pass in rounds. And I'm going to paste in the pseudocode and then we'll walk through it together. Okay, so let's start on our first line. We have a function defined as rock, paper, scissors, and it's taking in the number of rounds. We'll then create an empty array of outcomes to store the final result. And we'll also declare an array that will store all of the possible options for each round. So rock, paper, scissors. Then we'll move on to our helper function, which we'll call generate rounds. And this is the function that will recursively generate every possible sequence of throws. We'll have it accept two parameters. So the rounds left, which is the number of remaining rounds that need to be generated, and the current round, which will be an array that's tracking the sequence of throws generated so far. Our base case will be when rounds left equals 0. That means that we've generated a complete sequence of throws. When that condition is met, the current combination of throws will be stored in current round, and it's added to outcomes, which will then return and exit. Now below is our recursive case, which happens when there's still rounds left to generate. This is going to be the function that enters the loop and iterates through the three choices, rock, paper, and scissors. For each choice, the function is going to recursively call itself and then reduce the number of rounds left by 1 and add the current choice to the current round. Our initial call down here to generate rounds, this helper function, will start with a full number of rounds passed into rock, paper, scissors function and an empty array for the current round. That way we can begin building the combinations from scratch. And finally, once we hit our base case, we'll exit out and return the full list of generated outcomes. So now let's start on our code. The first thing we want to do here is create our empty array to hold our outcomes. Next, we want to create an array that will hold all the choices, rock, paper, and scissors. Next, we're going to define our helper function. So let's call it generate rounds. And we'll pass in rounds left, which is going to track how many rounds are left to generate, and current round. And that's an array that holds the sequence of throws that we've generated so far in the recursive branch. Take this curly brace and move it down here. Then we'll move on to our base case. So if the number of rounds left equals 0, I'll move this curly brace. Then we want to push the current round array into the outcomes array. So the outcomes.push the current round, and then exit the function. Now, if there's still rounds left to generate, we're going to enter our recursive case down here. So we'll create our for loop. We'll start I at 0 and go up to the length of our choices list. And we'll iterate incrementally. I'm going to move that curly bracket down here. Next, we want to call our helper function and then reduce the rounds left by 1 and add the current choice to current round. So our helper function is called generate rounds. I'm going to grab the rounds left -1 for our recursion. And we'll have an array here, and we'll use the spread operator to take all the elements in the current round array and spread them into a new array. So what's happening here is if the current round already has 2 choices in there, let's say it's rock, paper, and then the choices at element I is, let's say, scissors, it's taking current round, adding choices onto it to create a new array. So that would then be rock, paper, scissors with choices added to that. So after defining the helper function, we need to make an initial call to the generate rounds function, starting with a full number of rounds and an empty array for the current round, since we haven't generated any throws yet. So we'll do that down here. And we'll call our helper function with rounds and an empty array. And finally, once our base case is reached through recursion, we want to return our outcomes array. And then we're done. So now let's make one more pass through the code and see if we have any errors. So we have our function rock, paper, scissors. It's taking in rounds. We're initializing an empty array called outcomes, and that's where we'll store all possible outcomes. We're then creating an array that holds all the different choices, rock, paper, and scissors. Now we have our helper function, which is taking in the rounds left and also the current round. And our base case is if there's no rounds left, we want to exit out of that after pushing the current round to our outcomes list. While we're in our recursive loop though, we're going to start our index at I, move all the way through our choices list up through length. So rock, paper, scissors is our choices list. And we're iterating incrementally. And then our recursive action down here is calling the helper function, reducing the rounds left by 1 each time we go through, and then appending the current choice, so choice of I, onto whatever the current round is. And I noticed here that I have some brackets I don't need. And then to initialize the first call of generate rounds, our helper function here, we want to start with an empty array for the current round and the total number of rounds. After we hit our base case and we return, we want to then come over here and return our outcomes, which again needs a semicolon. So let's talk about the big O notation for the solution. The time complexity is going to be O of 3 to the nth power, where n is the number of rounds. The exponential growth here comes from the fact that for each round, there's 3 possible choices, rock, paper, or scissors. So for n number of rounds, the total number of possible combination of moves is calculated by multiplying 3, which is our choices per round, by itself n number of times. So that's what gives us the 3 to the nth power. In terms of space complexity, this is also going to be O of 3 to the nth power, and that's because of the fact that we're storing every possible sequence of moves into that outcomes array. Just like the time complexity, the number of sequences we store is going to grow exponentially with the number of rounds. Another thing with time complexity that we have to consider is the recursion stack. So while the recursion stack only goes as deep as n, because we have n recursive calls, the dominating factor here is still the number of sequences. So that's giving us the O of 3 to the nth power in terms of space usage. So our rock, paper, scissors solution here is efficient for small values of n, but as n grows larger, the exponential growth of the time and space complexity will lead to performance challenges. So today we learned how recursion works, by breaking a big problem down into smaller parts. We used recursion to generate the possible sequences of rock, paper, scissors throw based on the number of rounds that were given as an input. We also covered the two types of recursion, which is direct recursion, where the function is calling itself, and the helper recursion, where a nested function is doing the work. And while the solution works well for small inputs, we saw that the time and space complexity will grow exponentially as the number of rounds increases. Thanks for following along. I hope this helped.